Hello, I'm Professor Steve Honash at Penn State University, and welcome to the course Engineering Science 211, Materials, Safety, and Equipment Overview for Nanotechnology. We are beginning today Unit 2, which covers infrastructure. And this unit has the following outline. Today we will be discussing infrastructure. What is it? Why do we need it in nanotechnology? And then in subsequent lectures, we'll be discussing facilities and equipment systems. In the case of equipment systems, we'll talk about both vacuum-based systems and non-vacuum-based systems. So we're in Unit 2, Infrastructure, just beginning the unit with Lecture 1, What is infrastructure and why do we need it in nanotechnology? So let's begin with the definition of the word infrastructure. It's a word that you hear in common usage, and in common usage it means systems, equipment, services, and facilities. And that's what it means in nanotechnology when it's used by folks working in the nano field. It means systems, equipment, services, and facilities that enable nanotechnology. So when we use infrastructure, we mean the facilities used in nanotechnology, we mean the equipment used in nanotechnology. So why do we need infrastructure? And we'll go through this list as we proceed through the lecture. But obviously the first reason we need it is we have to have facilities and equipment. We have to have a whole infrastructure to actually carry out the fabrication. So we need infrastructure for the very obvious reason that we need some place to do our fabrication, to make our nanostructures, to make our nano products. Perhaps less obvious reasons for why we need infrastructure are these four others. We need infrastructure for contamination control. That's so important in nanotechnology, in nanofabrication. We need infrastructure for process control and for yield. And we need infrastructure for safety and protection of the workers. And finally, we need an infrastructure for protection of the environment. So these are the 5 reasons why we need infrastructure in nanofabrication. So let's talk about what is contamination. We said we obviously need infrastructure so we have a place to make things, but we also need it to control contamination. So let's talk about what is contamination. Well, it's a general term used to describe unwanted material of some kind that adversely affects the fabrication or synthesis of a nano product. And of course, just to remind ourselves of what we mean by nano product, let's remember that we're talking about something, whether it's a transistor, a sensor, whatever it is, that has at least one dimension in a nanoscale. And scale defines the effects of contaminants. In other words, the nanoscale is so small that something as simple as a dead bacterium is like a boulder. It's huge. So the scale that we're working at is so small that contamination can be extremely, and is extremely important. Contamination, as we see here, affects 3 major areas: processing yield, performance, and reliability. And we'll elaborate on these 3 areas now in subsequent slides. Let's talk about what the sources of contamination are. As we said, it's materials that just are inadvertently present. So you can have the materials that are used in processing be contamination. The processing equipment can cause contamination. It could be dirty. It could have a memory of what was processed in it before, which will then be the remainder of what was processed in the equipment before. It can be then a contaminant for a new process. The facilities themselves can be a source of contamination. And of course the people can be a source of contamination. and these are the things that we have to worry about that can contaminate a process. And we talked about the term processing. Usually folks say process control instead of processing control, but both terms are used. And process control requires complete command of the materials, structure, and dimensions of the nanoproduct being fabricated. In other words, at the nanoscale, you have to really be in charge. Can't leave anything up to nature, can't leave anything up to just chance. Have to be in complete command of the materials, the structure, and the dimensions of what you're making. So process control is extremely important, and that means that there can't be any contaminants getting into the process. So contamination has to be very carefully controlled. The process can have no uncontrolled elements. It has to be entirely controlled at the scale we're working at if we're going to get any kind of reasonable yield of nanoproducts. So here's this word yield. I just used it, and it comes up again and again. And let's talk about it. So let's talk about this idea of processing yield. Nanoproducts not turning out the way they should is loss of yield. So if every product turned out the way it should, the yield would be 100%. And yield is very, very important. Obviously, when you think about how much does it cost to make something, obviously you would like to have 100% yield so that your process is in complete control and there are no contaminants and every nanoproduct is turning out perfectly. So processing in a contaminated environment can cause a lot of problems which lower the yield. And for example, you can have, due to contamination, changes in dimensions, or you can have inadvertent altering of material properties due to contamination. So we've got to keep that yield up. And we have to then have very tight control of the process. We have to have very tight control of contamination. We can't allow it to happen. We can't allow these things to be out of control. Now, there are a number of in-process quality checks used in manufacturing to minimize contamination problems. Process lines constantly have checks going on looking for contamination. So this is a very important element of nanofabrication. Contamination results in fewer nanoproducts, as we said, completing the process. Contamination, therefore, leads to lower yields and higher production costs. So we have to control the process. We have to eliminate contamination. Performance, well, small contamination regions may escape in-process quality checks, that's possible, and seemingly clean materials can contain undetected contaminants that can change the performance of a product. So even though we're doing our best, we have to constantly monitor performance and make sure we have the processes, the various processes under control and contamination under control. So performance is the ultimate test. Is the product performing the way it should? If a product performs the way it should, then it's reliable. And the most serious of contamination-related problems is product failure. Lack of performing the way it should, that is, lack of reliability. And failure is a major concern, especially in areas when you're producing nanoproducts that are being used for medical applications, for space applications, for the defense industry. These can be particularly unacceptable. Reliability can also be a major concern in the consumer market. We as consumers, you and me, want our products to work. For example, if an unreliable cell phone, if you have an unreliable cell phone, that can cause a lot of consternation, and it can cause people to just go out and cancel their subscriptions. So there can be serious financial implications if there are reliability issues. So contamination affects device yield. It can affect performance. So the contamination is extremely important as we have to is part of a critical part of making sure we have complete control of a process. And the impact of contamination is a function of the size of the nanoproduct and the size, type, and concentration of the contaminants. So, as we said, the nanoscale is so small, very, very small. Contamination regions or contaminating particles can be absolutely critical. Well, let's just try to classify contamination. What are the types of contamination? So, for the purposes of discussion, we can divide contamination into the following categories. We can talk about contamination being films and residues. So I'm thinking about very thin films, perhaps with thicknesses in the nanoscale themselves. These films or film residues are certainly contamination. If there's something that's there, we don't want it there, and its presence is not in our control. Particles can be contamination. There's all sorts of particles. Some can be down in the nanoscale, and if they're there and we don't want them there, and we're not controlling their presence, that's contamination. Ions, which of course are atoms or groups of atoms that are charged, can also be contamination. Atoms of cells of different elements that we don't want there, that are there out of our control, are contamination. And so are molecules, same way. They're there, we don't want them there, they're uncontrollably present, that's contamination. And these contaminants can all be factors when undertaking fabrication at the nanoscale. In fact, they can be disastrous when undertaking fabrication at the nanoscale. Let's talk about films and residues first. As we said, these are thin layers, perhaps so thin that they're at the nanoscale themselves, and they can be on a sample, as I said, inadvertently and uncontrollably. And one example of a very serious source of contamination is humans themselves. The oil residues on our hands are very, very serious contaminants. Human hand oil is very difficult to remove, and if it gets on a product, it's there inadvertently, it's there uncontrollably, and it can totally ruin production and totally ruin the fabrication of a nanoproduct. So that's an example of a source of a residue, oils from human hands. So obviously, one has to be wearing gloves when undertaking nanofabrication. Particles. Well, we've talked about particles before. These are small objects, excuse me, that can adhere to materials and are the most common form of contamination. Airborne particles suspended in the air are known as aerosols, and an example of a source of aerosols is perfumes. So right away we think that if we don't want these small airborne particles, we're trying to really control that because we know we need yield, we need to have products that perform, then we know we have to worry about aerosols, and perfumes obviously are an example of a source of aerosols. So we can't wear perfumes when we're doing nanofabrication if we really want to control what's going on. Now there can be lots of different kinds of particles and a very wide range of sizes of particles. Here's a diagram that shows us relative particle sizes. And you can see it starts with gas molecules, and gas molecules are very, very small, tenth to maybe 1 nanometer. And I remind you that 1 nanometer is the same as, let's say, 10 atoms sitting in line. So 1 nanometer is like 10 atoms. So gas molecules can be made up of just a couple tiny atoms, or it can be made up of a number of atoms. And those are very, very small. Those are in the, let's say, 1 nanometer size range. Another common particle that one encounters in, obviously, nanofabrication is viruses. We know these are nature's nanoparticles, are all over the place, and the viruses can be in the 2 to 100 nanometer diameter range. Tobacco smoke, the particles, the aerosols in tobacco smoke can be in the 10 to 300 nanometer range. Bacterium, a bacterium cell, those can be in the 200 nanometer up to 10 micron range, so depending on the cell size. So as I mentioned earlier, those can be boulders. Tobacco smoke particles are boulders. Viruses are boulders if they get onto a product during its fabrication, during the processing steps. Fog, just to again give a picture of particle sizes. Fog particles, the water particles in fog, can be 1 to 50 microns in size. And a human red blood cell is about 7 to 8 microns in size. And then, for example, another particle that we commonly encounter, dust particles, pollens, these are 5 to 50 microns. Human hair is 50 to 120 microns in size. These are diameters. And then beach sand, just to complete our picture of the particles we see all around us, or have all around us. Some of these we can't see. Beach sand is about 100 microns, and even larger. So lots of particles floating around. Look at these particles. I mean, these are just in the environment without doing any kind of nanotechnology. These particles are there, and for us, trying to make nanoproducts, these particles, if they're inadvertently present, if their presence is out of control, these can be disastrous. Here's another diagrammatic depiction of particles, and this one shows the relative size of particles. You can see the different sizes. There's a human hair. There's a particle that's the black dot. That represents a particle that's 10 microns in diameter, so you can compare it against the human hair. The dot up above, that's a particle that's 500 nanometers in diameter. So this is obviously not to scale, but it gives you an idea of the different sizes of particles. Ions. So let's move to ions, another source of contamination. And mobile ion contamination, that is ions that move around. They can diffuse, or they can move in electric fields. The reason they can move in electric fields, of course, is because they're charged, positive or negatively charged. They can contribute to corrosion, and since they're charged, they can alter electrical characteristics, which can then change performance and reliability. Common mobile ionic contamination arises from group 1 ions. And of course, by group 1, I mean group 1 of the periodic table. Mobile ionic contaminants, well, as we said, ions are atoms or groups of atoms that are charged. And only a small concentration of mobile ions, say 10 to the 10 atoms per square centimeter, is needed to start causing problems, for example, in electrical devices. Because if you sit back and calculate how many atoms there are on a surface, it turns out that there's 10 to the 14 atoms per square centimeter. That number is pretty darn true for just about any material. Oh, okay, some materials it might be 5 times 10 to the 14, some it might be 9.8 times 10 to the 13. But the point is, there's around 10 to the 14 atoms on a square centimeter of any reasonable material. And so if you have, let's say, if I take that number, 10 to the 10 ions on a surface, you can see that 1 out of every 10,000 atoms is a contaminant. So 1 out of every 10,000, that can be disastrous for electrical devices. So for example, for transistors, that kind of contamination is positively disastrous. And it doesn't take much, only 1 in 10,000 atoms, to cause a disastrous situation from this source of contaminant, mobile charge, mobile ions. And these ions are very mobile. They can move through an electronic product even after passing electrical testing and shipping, and they can cause failure in the field. And the group 1 elements, such as sodium, potassium, and lithium, these are the common culprits causing this kind of ion contamination, which is particularly disastrous for electrical devices. And just to talk about these impurities, for example, metallic elements often can be ionized, and iron, copper, aluminum, chromium, tungsten, and titanium. If those are present in some way in a contamination, if they become ionized, they can become very mobile, and the others we mentioned, sodium, potassium, and lithium, are extremely mobile also. Now, many of these elements, such as iron, copper, what have you, are found in biological systems, potassium, sodium, and so they can be present. They can be present in human breath. They can be present on people's hands because they're just part of a lot of biological systems. So these metals, which can be easily ionized, can be quite a source of mobile ion contamination. Well, atomic, molecular, thin film, and residual contamination, where does it come from? Well, I keep incriminating humans. You can see humans on the list here, but the list actually is pretty extensive. The actual processing, the actual making of things, the tools you use, the equipment that you use can be a source of contamination. And the chemicals that are being used, even including DI water, if it's not being properly monitored, can be a source of contamination. Remember, DI water should be 18 megaohm centimeter to be really good deionized water. And it also has to be free of viruses and bacteria. And so you have to really make sure that the DI water, as is the case for all chemicals, that the purity is very carefully controlled. And chemical reactions can take place on surfaces that produce byproducts that can become contamination, or are contamination. The environment, we just saw all those different kinds of particles, dust particles, pollen. So the environment can be a very significant source of atomic, molecular, thin film, and residual contamination. And of course humans. And as I said, I've been incriminating humans a couple times here now, so I won't say anything more about that. I will mention, though, that contaminants can be organic or inorganic. And let's look into that a little bit further. First, I think we need to talk about, we say organic, inorganic. What do we mean by an organic, for example? Well, the term organic refers to some material, some chemical, that's generally used in some sort of a fashion, in a product, in a reaction or something. But it does not, but it does, contain carbon. That's the telltale distinguishing feature of an organic. It contains carbon. There are some exceptions to that. For example, diamond is not considered an organic, nor is graphite, nor is graphene. And I'll just remind you that graphene is a single sheet of graphite. Now, I just want to comment that you will find more specific definitions of organic. Sometimes you'll see definitions that say organics contain carbon, hydrogen bonding, and there are some other variations. But the one that we have here, that it's generally used to refer to any compound containing carbon, with those exceptions. That definition is the most general, the one that's in general use. So organic contaminants, let's use that definition. Organic contaminants can include molecules, thin films, residues left behind by processing or some other exposure. Now again, I remind you that contaminants may not just necessarily come from humans or the environment. We had that list a couple minutes ago. the processing itself, the equipment, the chemicals, can produce contamination. Typical organic contaminants, well, obviously bacteria, if there are dead bacteria cells or any kind of bacterial cells, processing residues, lubricants, vapors, detergents, solvents, virus molecules. These are typical examples of organic contaminants. So bacteria, for example, I mentioned their possible presence in BI water systems. They can grow in the water systems and on surfaces that are not cleaned regularly. And if they are present, bacteria can act as particulate contamination. The actual bacterium cell is obviously a particle, but the bacterium can disintegrate and it can contribute to organic and metallic ion concentration. So it can produce metallic contaminants and it can produce metallic ion contaminants also. Inorganics, let's just complete this organic, inorganic definitions, the set of definitions. The term inorganic generally refers to any substance not containing carbon, but then of course you have the analogous exceptions, which are diamond, graphite, and graphene, which do contain carbon but aren't considered inorganic. So that's the most general definition of inorganic. It's something that doesn't contain carbon with those exceptions. Now, inorganic contaminants include atoms, molecules, thin films, residues, again, left behind by processing, left behind by some chemical reactions, or something that comes out of the environment, or any other exposure that can produce contamination. Sources of contamination, then, just to re-emphasize this, literally everything that comes into contact with a product during its manufacturing is a potential contamination source. Whether it comes from the environment, from humans, from the equipment, it's a contamination. Anything that comes in contact is a potential contamination source. So just to summarize what we've been saying, the major contamination sources are air. We talked about pollen and dust and viruses. Processed water can be a contamination source if not carefully monitored. Equipment that you're using to fabricate nanoproducts can be a source of contamination if not carefully taken care of. Processed chemicals, if they're not of sufficient purity, can be a source of contamination. Processed gases, again, if not of sufficient purity, can be a source of contamination. And of course, humans, personnel, as we've said several times, can be a source of contamination. The air, let's talk more about the air. A lot of particles, aerosols, must be treated before entering a clean room, for example, or before it's used in any controlled environment, like a chemical hood. So you can be doing your processing in a hood, but the air in that hood needs to be free of particulates and aerosols. You can be doing your processing in a clean room. The air in that clean room needs to be free of particulates and aerosols. Air cleanliness levels. So we really need to keep air clean. We need to be able to talk about how clean the air is, whether it's being used in a clean room or a hood, wherever it's being used, we must be able to quantify how clean the air is. And that's done by talking about the particulate diameters in the air and by talking about how many particulates there are per volume, say per cubic foot, per cubic meter, whatever. Usually per cubic foot is used. And usually air quality is identified by something called class number. And this particular definition, or this particular way of monitoring air quality, is defined as the number of particles of a specified diameter in a cubic foot of air. So class number is defined as the number of particles of a specific diameter in a cubic foot of air. So here's a table that talks about this class terminology. So it's based on particle size and density limits in a clean air environment. And it comes from a federal standard, as you see there, and we'll talk about the federal standard in just a minute, but let's take a look at some of these definitions that you see on this table. So, for example, Class 1, this is the most stringent classification for air, whether it's air in a clean room or air in a hood. If it's Class 1, then that means that there are less than 35 particles which have a diameter of 1/10 of a micron. So it has to be less than 35 particles that have a diameter of 1/10 of a micron. Remember, 1/10 of a micron is 100 nanometers. And it also must have less than 8 particles whose diameter are 200 nanometers. It has to have less than 8 of those. And it must have less than 3 particles whose diameter is 300 nanometers. And it must have less than 1 particle whose diameter is 500 nanometers, half a micron. And there must be less than 1 particle that is 500 nanometers or larger. So it has to be less than one of those. So the fifth column over here, 5 microns, doesn't come into play because the previous column says that there has to be less than 1 particle, 0.5 microns or larger. And then you see the definition of Class 10, of Class 100, Class 1000, Class 10,000, Class 100,000. Let's look at Class 1000, for example. That requires that there has to be less than 1,000 particles whose diameter is 0.5 microns. It has to be less than 1,000 of those whose diameter is 0.5 microns, or it could be smaller. And there has to be less than 7 particles whose diameter is 5 microns. So you see these different definitions, and these definitions are for a cubic foot. So these numbers, these densities, are specified for the number of particles in a cubic foot. And just to give a sense for these class numbers, if you were to be in a farm area, rural area, the class, using this kind of classification scheme, would be Class 2 million. And if you were in a city, the class would be about 5 million. And a typical hospital operating room is to also further quantify or further calibrate you. A typical hospital operating room is about Class 100,000. Federal Standard 209 was first published in 1963 in the USA, and when it was published it was titled Clean Room and Workstation Requirements, Controlled Environments. And it's been revised several times, as you see, and if you're interested in further examination of this standard, you can go to this site that is mentioned here below at the Institute for Environmental Sciences. Now there's another scheme used to talk about room cleanliness, and this one is defined in a metric, using a metric volume. Is defined as the maximum concentration limits, that is the particles, it's defined in terms of particles per cubic meter, for particles equal to or larger than the considered sizes shown below. And these are called the ISO numbers. So instead of classification Class 1 or Class 10, these are ISO numbers, an alternative way of classifying, quantifying the cleanliness of air. And you can see ISO 1 standards, ISO 2. So ISO 1 standard, again, that's the cleanest. There can't be more than 10 particles that are 100 nanometers or larger, and there can't be anything more than 2 particles that are 200 nanometers or larger. So very stringent conditions, and you can see this is goes all the way up to ISO standard 9. And the definition of that is given in the last row. And just to mention to you what ISO stands for, it stands for the International Organization for Standardization. So the letters aren't arranged in an English fashion. It's an international organization. So it's ISO, but it stands for International Organization for Standardization. Well, let's talk further about some of the other sources of contamination. There's processed water, we've mentioned, very, very important. You have to obviously have 18 megaohm centimeter water, deionized water. It has to be devoid of any viruses or bacteria cells, so you have to be very careful of processed water. It can be a major source of contamination. As we said, equipment can be a major source of contamination. The equipment may have some material left in it from some previous process step, which you do not want to be involved in the next process step, or you do not want to be present because it can chemically react with whatever you're doing in a given process. So the equipment can be a reservoir of contamination. It has to be very carefully cleaned and monitored. And processed materials and chemicals can be a source of contamination because they're not pure enough, or because perhaps there's some chemical reaction that takes place, leaving contamination as a byproduct that you're not aware of. So you have to be very, very careful of processed materials and chemicals. And processed gases can be a serious source of contamination if their purity is not sufficient, if when used in some process step they produce byproducts that you're not aware of, that you don't want, that are uncontrollably present. That is a very serious source of contamination. Well, as we said, people are a major source of contamination, and let's we go back to that idea. So we really have to make sure that we can isolate humans from the nanomaterials and the nanoproducts that we're working with. So depending on the situation, people need to be covered in special clean room garments known as bunny suits, which consist of a hood, face mask, coveralls, boots, and gloves. Now, this is if you're going to use a clean room. If you're going to use a clean hood, then perhaps a full bunny suit is not needed because there's less chance of contamination. But each situation has to be evaluated itself, and you have to make sure that people are not a major source of contamination. If they're walking around inside a clean room, they have to be very, very carefully covered, and their potential contamination impact has to be carefully controlled. If they're working by a clean hood or a glove box, perhaps they don't have to be fully have full fully complement of garments, but you still have to make sure they're not impacting the process. So what is the problem here with humans? Well, we've mentioned hands in the oils on the human hand, but there's also other sources of contamination. Hair and skin. Skin is constantly flaking, and those flakes can be boulders at the nanoscale, so we have to watch out for that. Hairsprays. Folks use hairsprays. That can be a source of aerosols. The aerosol particles can be huge. Remember, we're at the nanoscale here. We're making things that are so small that a tiny little aerosol particle floating around that lands on our product can be disastrous. Cosmetics can be a source of particles that are serious contamination. Facial hair, another source. Exposed clothing, the clothing itself can be giving off particles. And then human respiration as a large source of particles. So talking about respiration, we take a look at this way that humans not only generate particles by respiration, but actually propagate those particles around in an environment. So for example, if one is talking normally, such as I'm doing right now, saliva can be projected out 2 to 3 feet. And obviously these saliva particles are very small. I'm speaking right now, but I don't think I'm spraying anyone with saliva, but I'm producing tiny particles, and those can travel out 2 to 3 feet. And again, those tiny particles can be viewed as boulders at the nanoscale. A person coughing produces saliva particles and even lung tissue particles, and those can be projected 4 to 6 feet. And a person sneezing, that can result in a projection of 10 to 15 feet at speeds up to 200 miles an hour, and huge particle emissions. So obviously someone sneezing in a class 10 clean room is just can't have anything like that. All of these things have to be controlled, have to be removed from the environment in which you're trying to do nanoprocessing. If you're trying to get yield, if you're trying to get device product performance. So just looking a little bit more at human contamination, spittle, or whether you call it spittle or spit, saliva, that contains potassium. We mentioned potassium when we were talking about mobile ions. Contains chlorine, phosphorus. Here's another possible source of mobile ions. Sodium, we talked about, big source of mobile ions. Respiration, look at these. Sodium, mobile ions, potassium, mobile ions. You got possible mobile ions. Lots of different impurities here that comes from perspiration. Dandruff, calcium, chlorine, carbon, nitrogen, cosmetics. Oh, look at all these sources of possible mobile ions. And just general rich supply of contamination. Fingerprints, that's the finger oils I was talking about. Sodium, so mobile ions, potassium, chlorine, phosphorus. All those things can be in the human oils, along with organics. So humans really have to be carefully controlled if you are going to have process control, if you're going to have yield, if you're going to have contamination control. In some situations, in some areas of nanofabrication, humans are almost entirely removed from the situation. I just recently toured a nanofabrication facility being used to make optoelectronic devices, and everything that was done there by robots, and the humans were just there in case some trouble developed with the equipment. They weren't touching any of the processing at all. So here's an analysis of cosmetic particles produced by cosmetics getting into the environment. And you can see lots of the things that we just talked about: sodium, you can see magnesium, gold, even gold, palladium, titanium, iron, potassium. This is done by looking at energy dispersive X-ray analysis, EDX. So what happens is you send in the energetic electrons into a sample, and then you look at the X-rays that come out, and the X-rays are used to fingerprint what element they're coming from. So energetic electrons in a scanning electron microscope, out comes the X-rays. The X-rays are used as the way to identify what's here on the surface, and you can see some contamination on the surface from cosmetics. We'll be talking about these kinds of characterization techniques as we get into our survey of equipment. So protecting the nanofabrication environment from human contamination, obviously you have to, depending on the situation, if it's a clean room, you need clean room garbs, clean room garb, clean room garments. If it's a hood, you don't need as extensive clothing, special clothing. So you have to adjust for the situation. But whenever the humans are in contact with processing, you have to worry about this human contamination issue. Now, if you are using a clean room, where the whole volume is the air is carefully purified, carefully cleaned, and we'll get into that in a minute. If you are using a clean room, where the whole volume is carefully monitored and kept clean, and then you really have to isolate the human. And you have to make sure that the human is wearing clothing, garments that make sure that there's no body-generated particles or aerosols that are being liberated. Make sure that the garment itself isn't releasing any particles. You have to worry about making sure that the human isn't generating any electrostatic charge. Let me come back to that a minute. I think we're all familiar with walking across a rug in certain situations, such as when the humidity is low, and generating an electrostatic charge. Just walking across a rug and then you touch something, and there's a discharge from your hand to whatever you touched, or from whatever you touched to your hand, depending on the charge flow. That's called an electrostatic discharge. Well, that's sort of a kind of contamination because it can cause a lot of damage. And so you have to make sure that there's not this situation where electrostatic charge can be built up by the human walking around. The human touches something that there discharges, and that inadvertently affects the product you're trying to make. It all gets down to this issue that the whole processing sequence, whatever you're doing, has to be completely under control. There can't be something happening like an occasional electrostatic discharge. You can't have that. You can't tolerate that. Everything has to be under control. So even humans walking around can't generate charge, and as you think of the human's attire, you have to be making sure that attire prevents that type of situation. And of course, the attire, the garb, can't allow release of chemical or biological residues. So here's an example of a bunny suit, a clean room suit. You've got the cap. Very important that you have the safety glasses, the mask, making sure no particles are coming out. Also, you don't want any particles to be respirated into the human either. So that mask serves a dual purpose. You obviously don't want to get residues onto products. At the same time, you don't want any chemicals to get onto the human. So these kinds of gloves can be very important, and shoe covers, and the overall bunny suit. So when you're suiting up, this is the sequence. Put the shoe liner, the shoe covering on first. You have to make sure that you don't have any personal items. Don't want any fuzzy sweaters or fur or jewelry. Like to keep the jewelry down. No cosmetics, no perfumes. We talked about aerosols several times. Contact lenses. You want to wear safety goggles. You don't want to bring medications. Obviously, no chewing gum, food, drink, tobacco. You know, this is a very big part of working in this industry. You have to realize the discipline that's required and the professional environment that one is working in. It's like working in an operating room. You can't be there with chewing gum, drinking. It's a very carefully controlled environment. You obviously can't have dirty or torn gowns. The gown is another term for the bunny suit. And then this is the order in which one suits up, starting with the head cover, the shoe cover, the gloves, the hood, the boots, the clean room overalls, that is the bunny suit or the gown, the safety goggles, very important. And then oftentimes a second pair of gloves is required in case the first pair got contaminated in doing these steps, a second pair before you enter the clean room. And of course, can't have any hair, facial hair, or beard or mustache exposed. So you have to do all these things to keep the environment, the manufacturing environment, under control. And then you also have to worry about having infrastructure that makes sure that the workers are safe and protected. So you have to make sure the clothing also serves to protect the workers. So the gloves in this have to be designed for the situation. If you're doing chemical work with dangerous chemicals, you need to wear heavier gloves. You need to wear special aprons if you're working with dangerous chemicals. You need to worry about masks in case of respiration might be an issue, as well as the usual mask to prevent saliva particles from coming out. But you also have to worry about respirating dangerous particles in. So you have to worry about masks, obviously eye glasses to protect the workers' eyes. Of course, part of the infrastructure in a clean room facility, or even in a facility that just has chemical hoods, part of the infrastructure is to have eye wash stations, showers, alarms. The infrastructure must make sure the worker is safe and the worker is protected. And of course, you try to keep you must keep the processing away from the worker. So the processing is done in hoods, maybe done in glove boxes, or perhaps even in a clean room. So you're trying to protect the worker, and you're trying to, at the same time, create an environment where contamination is under control, and you have good yield, and the process is under your command, and you know exactly what's going on. So you have to protect the humans, you have to create the correct environment. That's the job of the infrastructure. And the infrastructure, of course, is made up of filters, both to clean the air, to clean the environment, but also to make sure that particulates are taken out to protect the humans. And of course, there has to be radiation protection for the humans around different kinds of equipment. And we'll talk about that more as we get into equipment, but you have to make sure that the infrastructure protects the workers from any radiation sources. And you have to make sure the infrastructure protects the environment. So you have to look at issues like materials and liquids that are left over from processing have to be properly collected and disposed of. And effluents, be they gaseous or liquid, they have to be purified in some way. There has to be systems for this. And one must make sure that the infrastructure also protects the environment. Well, we have completed Lecture 1 of Unit 2, and we've talked about what is infrastructure and why do we need it. And we've gone over these topics. First of all, we said the obvious. We need infrastructure because we have to have some place to do the actual fabrication, where we have to make things. We need some place dedicated to that. So that's obviously a very basic reason why we need infrastructure. But more importantly, we needed, or less obviously, I guess would be a better way to say it, we needed for contamination control. This is crucial. And we also need it for process control and yield. We have to be in control of the process all the time. There can be nothing left to chance. And we have to try to get the yield, well, ideally at 100%. And then we have infrastructure for the very important reason that we're very concerned with the safety and the protection of the workers. So infrastructure is needed for that. Infrastructure must ensure that. And finally, we discussed that we need protection of the environment. So the infrastructure must achieve that also. See you next time when we move to Lecture 2 of Unit 2.